In this video, we're going to learn more about the Bohr model of the atom. We'll also learn how to draw orbital diagrams and understand why we sometimes see flashes of colors when we excite electrons of certain types of materials, and why we get distinct color patterns for that. So orbital diagrams are diagrams that show the distribution of electrons in their orbitals. We sometimes refer to them as arrows and boxes diagrams. If you remember from our last lesson, we talked about how two electrons in an orbital can't have the same quantum number, and that they have different spins. So one of them will spin clockwise while the other one will spin anti-clockwise. So we represent that by drawing an arrow pointing up and an arrow pointing down as representing each of the electrons. You can draw them as half arrows like this or full arrows if you wish, but that's how you do it. And then what you do is you record all of your orbitals vertically, and then you draw boxes to represent each of the suborbitals. Starting at the lowest energy level, so 1s, 2s, 2p, and so on. So if we were to draw for carbon, remember, has 6 electrons, so the first orbital is 1s, and you would draw one arrow up, one arrow down. 2s would be one arrow up, one arrow down, and then remember there are 3 suborbitals for p, so you would draw the 3 boxes, and then you would draw 2 electrons. So remember for this as well that for carbon, you end up you don't double up, using HUND'S rule, you don't double up electrons until you are finished putting singles in. So nitrogen is 1 over from carbon, so its electron configuration is 1s2, 2s2, 2p3. So it's probably best if you do the electron configuration before you draw these diagrams. So 1s2, 2s2, and then 2p3. Oxygen is the next one over, so 1s2, 2s2, and then 2p4. So you'd put 1, 2, 3, and then you put your 4th one, like so. And if you were going to do the next one, fluorine, you would put there, and then neon would have another one there. So as I said before, HUND'S rule says that you need to, well, first of all, you should draw your electron configuration, and you fill the electrons from the bottom to the top, and HUND'S rule says you must add an electron to each orbital in an energy level before you double up. So in our example, we're being asked to draw the energy level or orbital diagram for fluorine. So we'll draw the electron configuration first for fluorine. So fluorine is 1s2, 2s2, and then 2p5. So there's 9 electrons in fluorine, so that's where we get our electron configuration. So now we'll draw our boxes. So we'll start down here. So one box for the 1s. We'll draw a box for the 2s, and then a box for the 3 boxes for the 2p. So now we'll draw our arrows. So 1, 2, 3, 4. We fill those ones. 5, 6, 7. Now we start doubling up. 8, 9. So that would be the orbital diagram for fluorine. Our next one, we're being asked to draw the energy level diagram for argon. So argon, for these ones, it's probably best not to draw the condensed form because you need to know the distribution for each. So argon is 1s2, there's 18 electrons by the way, 1s2, 2s2, 2p6, so that gets us to 10. Then we have 3s2 and 3p6. That will be our 18 electrons. Now we'll draw our boxes. So first I'll draw the 1s, and then our 2s. 2p, remember, has 3 suborbitals, so 3 boxes. 3s has 1, And then 3p has 3 boxes again. So now we'll fill them up. And this one is actually going to fill up completely. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So that's the orbital diagram for argon. So now we're being asked to draw the one for calcium. So calcium has 20 electrons. So 1s2, 2s2, 2p6. That is the first 10. And then 3s2, 3p6. That's our next 8. So we have 2 more. So 4s2. And that makes sense because calcium is in the 4th period, so the 4th energy level, and 2 over, so 4s2. So now we'll draw our boxes. So 1s, 2s, 2p has 3, 3s has 1, 3p has 3, and then 4s. So we'll start filling. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. There's calcium's orbital diagram. So right now we're going to learn a little bit about the electromagnetic spectrum, which should be reviewed from grade 10. We sometimes also call it light energy. And light energy travels at 3.0 times 10 to the power of 8 meters per second, so travels at the speed of light. It travels in waves, but it also travels in straight lines until it hits something. So whether it hits something and passes through, if it's refracted, or if it hits something and is reflected. Again, we learned about that in grade 10 optics. Light also, or electromagnetic spectrum, travels in bundles of energy called photons. And some examples of the electromagnetic spectrum would be visible light. That's the range of wavelengths that we can see. Then there's infrared light and UV light. Infrared light has a longer wavelength and is lower energy than the visible spectrum, but we still can't see it. And then UV light has a shorter wavelength and has a higher frequency and more energy than the visible light spectrum. And we'll refer to both the infrared and UV light spectrums when we talk about emission spectra. So this is a representation of the electromagnetic spectrum. So this is the range. So high frequency waves have a very short wavelength, so very short distance between the peaks. So that would be gamma rays, X-rays, and UV light all have high energy, and they become further and further apart and increasing the wavelength as you move to the right, but then they are also decreasing in energy. So gamma rays, not good at all. They're 10 to the power of 20 hertz. Hertz is the number of cycles per second, how long it takes or how many waves you have per second. This one here, X-rays, we've been exposed to them when we've had X-rays on our teeth and so on, but again, long-term exposure to X-rays can be very bad for your health. Ultraviolet rays are less energy than X-rays, but they still can be detrimental to our health if we are exposed to UV radiation too much. That's why we wear sunscreen and sunblock when we have to be out in the sun. This tiny little box right here that's been expanded is the range that we can see. So humans can see from between 4 times 10 to the negative 7 meters all the way up to 7 times 10 to the negative 7 meters. So this is the only wavelength range that we can see, and it breaks apart from violet all the way down to red, and that makes sense. UV, ultraviolet, is just to the left of that, so a little bit more energy, 10 to the negative 8. And then infrared is just past what we can see, so in the red range. And then there's microwaves and radio waves. So this is an illustration of the electromagnetic spectrum. So we'll talk a little bit about wavelength and frequency. So wavelength is the distance between two waves. Its symbol is lambda. Looks like an upside down Y. So this would be, you'd measure the peaks of two waves and find out the wavelength. If you have a long wavelength, you have low energy. And then, so this one would have a lower energy than this one. Frequency is the number of cycles per second, and that symbol looks like a V, but it's actually nu. It's the Greek letter nu. And the higher the frequency, the higher the energy, and the shorter the wavelength. So this one has a shorter wavelength, so its frequency would be higher than this one here. So the continuous spectrum is called the continuous spectrum because all of the colors blend together and there are no interruptions or gaps along the way. So, however, when electrons get exposed to electrical current, you would think you would see a continuous spectrum, but instead you see distinct colored lines separated by spaces of varying lengths, and that would be an absorption spectrum or a line spectrum, and we're going to take a look at that. So this would be your continuous spectrum, what you would expect to see, but when you show or pass electricity through, there are parts where the electrons are absorbing the light. So then you have these like interruptions. So the absorption spectrum has these little black bands, and it's showing what light is being absorbed by the electrons. An emission spectrum is what gets reflected back. So we're going to learn about what this actually means in just a little bit, but you'll see this is the absorption spectrum for hydrogen, and this is the emission spectrum for hydrogen. And you'll see as you're looking at the spectrum, the wavelengths are getting smaller and smaller, so the lines for the colors converge on each other. So you have quite a bit of space for the red range, not very much for orange, yellow, green, blue, and so on. So the lines begin to converge as the energy gets higher. So that is something that you really have to remember for IB assessments. That as the energy increases, the lines in the emission spectrum converge together. So now we'll talk a little bit about Bohr's model. So Bohr believed that electrons orbited the nucleus like planets around the sun. We know that's slightly different, but he did say that there were distinct energy levels, and that the energy of an electron was quantized. So at these energy levels, the electrons had specific values of energy. So at n equals 1, that is lower energy, to be higher energy, and so on. So the energy increases as you go out and orbit. So sometimes we talk about excited state and ground state. So if an electron absorbs light energy, it'll become excited and jump to a higher energy level, and that's the excited state. So for the electron to go back to its correct orbit, it has to release that energy in the form of light and go back to its ground state. So when it's jumping up to the higher energy level and absorbing energy, that would be where you would see the absorption spectrum. When the electron's coming back down, it's releasing the energy, and we can see the bands of color for those electrons jumping back down to their ground states. So if an electron absorbs a photon, the electron jumps up in orbit, or more, that's the absorption. And then if the photon is released, we can see the light and it moves down in orbit. So that would be the emission. So again, we'll take a look a little bit more in depth for an absorption spectrum. This would be the absorption spectrum for hydrogen. So remember, n equals 1 is the ground state, but that we cannot see. We'll talk about that a little bit later. This is n equals 2, so it's the electrons are absorbing energy, and when they jump to different energy levels, they're absorbing different wavelengths of energy. So when it jumps from N2 to N3, that's red light being absorbed. N2 to N4 is lighter blues or cyan, and then blue up to N5, and all the way up to N6 is ultraviolet or violet. And you can see, like I said before, as you go further and further, higher energy waves being absorbed, you see that the lines are starting to converge. So emission spectra are drawn or represented when electrons are jumping back down to the second main energy level from the higher energy level, and when they do that, they release light. So we can't see in this range, and we can't see beyond n equals 2. N equals 2 is our visible range. So if we look at from n equals 5, jumping back down to n equals 2, we would see a line in the blue region. N equals 3 to n equals 2 would be red, and so on. So this is just the reverse of the absorption spectrum where those black lines are. Now we see actual representations of light. And as you move to higher energy levels, like in jumping back down, you can see that the lines are converging at the higher energy wavelengths. So these would be the higher energy wavelengths, jumping bigger gaps than here. So for your IB exam, you're required to understand the absorption and emission spectrum for hydrogen. So those last two examples were the absorption and emission spectra for hydrogen. But we'll look a little bit deeper here. So we have our line here of increasing energy, and then n equals 1, the ground state. Each of these, n equals 2, n equals 3, 4, 5, 6, and so on, these are the excited states. For this one, if you take a look, the reason why we don't write anything in the ground state, n equals 1, when those electrons are dropping back down, that's UV radiation. We can't see in that area. So we don't see anything when the electrons are jumping down to the ground state. We do see them when they jump down to n equals 2, because that's the visible light spectrum. N equals 3 is infrared radiation, so we can't see these either. So these electrons are jumping down, but the only ones that we can see are when they jump from higher to lower to n equals 2. So this is the region that we can see to the visible light. So if we go back to our emission spectrum and eliminating these parts where we can't see, this is what you would need to draw. So you might be required to draw the energy line here. N equals 1, you would label and write that that's the ground state. N equals 2 is where you would be showing the electrons jumping down. N equals 3, N equals 4, N equals 5, N equals 6. They get closer and closer together as you go further and further out. So this doesn't have to be precise, just showing that they are converging. The emission spectrum, you would show jumping back down. If you were asked to draw the absorption spectrum, you would show the arrows going up. So you would have one going from N to 2 to 3, and then you would have one going 2 to 4, 2 to 5, 2 to 6, and that's hydrogen's emission spectrum. And you'll see that they're converging because as you move to the left, you're increasing the wavelength and the energy, or decreasing the wavelength, increasing the energy, so they're starting to converge. So this diagram you need to be able to reproduce on a test or assessment.